So remember that by joining your recording, you can turn your camera on if you want, because the cameras are not going to be recorded, in case you want the conversation to be a bit more human. Welcome. So the name is Ray Cabello. Some of you might know me already. I'm a software consultant. I have been working in .NET mostly most of my career, but it's not the only stack that makes me suffer regularly. I'm also working with the Node, and I also do performance there. But .NET has been recently one of the things that I have invested the most time when it comes to high performance. And what I want to share with you today is not just a story about how to measure performance in .NET and how to improve based on what you're making readings on that, but also how to develop a system to help you understand what's going on in your measurements and in your head when you're making this kind of improvements. Because we have, let's say, certain limitations when it comes to understanding how a system is performing. We'll get to that in a minute. So what I'm going to go over today, just 3 points. I didn't want to overload this. So we're going to go first about measuring, and measuring includes a little bit of fixing and techniques to work based on what you have measured. We're going to go over how intuitions can be a dangerous friend to have when it comes to that. Experience can play against us when working with performance, and how our ego and our emotions can pile on top of that, making us believe that what we think is what we should do next. It's probably not. Okay, so let's start with measuring. I wonder, some of you have heard a phrase by Donald Knatt. It's a famous paper that he has on performance. And anytime someone asks and suggests to make a change because things might add better, I think that we have all had this quote sent as us to stop premature optimization. And the phrase says something like that, something about premature optimization, that you go to reject an idea that sounds like too much work. For the life of me, I think that some people believe that this is what actually says in the quote by Donald Knatt. Evidently, that was just a silly joke, but there is a phrase in that white paper that says that we should forget about small efficiencies, say about 97% of the time, because premature optimization is the root of all. Okay, then there is a small group that can be even more obnoxious, that will go with the second part of the quote that some people remember, which is, yet we should not pass up opportunities in that critical 3%. This is the important part. Whatever you guess that is your critical 3%, most of the time you're going to be wrong about it. That's why we're here, and that's why measuring tools are so important. Because the white paper continues, it's not a one phrase thing. And there's one point where he explains that most of our intuitive guesses fail. And this is not the intuitive guesses of people that have not done any performance improvement ever. These are the intuitive guesses of people that have been working in high performance environments for decades, and yet your instincts fail. I'm going to quote one person in this call, actually, and if you want to say that it was you, you can say it, but if not, not. I was working in a project where I found that we were making calls to the database. We will get a list of elements, and then we will make one request per element to the database. And we all been there. I don't know if maybe not everybody, but most developers will have hit a moment in their career when they find that something is underperforming, and it's because we need to fetch data from a list of elements, and we make one query per element, one round trip to the database per element, and we say, well, we can optimize this by making a single trip. Does it ring a bell? Sounds familiar? I would like, yeah. Jorge Mora has raised his hand. Oh, it means that it rings a bell. Yeah. Okay. Yes, great. Rings a bell. Fantastic. Well, the thing with this is that I presented this idea to the team lead and that company at the moment, and I said, we have this, we're making these calls. If we transform the repository to be able to make a query for all of the elements, we do only one round trip. This could save a lot of time in this endpoint when we're running this function. And I gave a full explanation on how long will it take, what to do, and his answer was, do we have a performance problem in that endpoint? Everybody has a plan until they get punched in the face, quoting Mike Tyson here. That's how I felt at that moment. I felt like I was getting punched in the face because we did not have a performance problem in that endpoint. That endpoint was getting static data and is when it was being cached. So we will only make that query once every 5 minutes. Not a big deal. Right. So what is this critical path thing? I'm going to go with another quote. There's a few. I think this is the last quote that you're going to hear, and it is a capital mistake to theorize before you have all the evidence. It biases the judgment. This is from Sherlock Holmes. What's the problem with this quote? As much as I like it, and as much as I like Sherlock Holmes, is that how do you know that you have all of the evidence? I have bad news for you. You don't. You don't know if you have all of the evidence. You gather as much evidence as you can, you develop a hypothesis, and you try as hard as possible to prove yourself wrong. How do you gather evidence? Well, there's a series of tools in .NET that help you understand what's going on in your system. And some of you that have worked in the cloud, that I know some of you have worked in the cloud, you might notice that there is no observability in this list. No Grafana boards, no New Relic or any of these companies that are not sponsoring me, definitely. It's not in this list. And there's also other tools that could belong to that list, but I'm just listing here the ones that I'm going to talk about today. And I'm not even going to show tracing or allocation tracing in depth. I'm just going to mention them, and I will do one allocation tracing to show how it works because of time constraints, evidently. And the reason observability is not here is because the metrics you get from observability are like the recording of a car race when you are part of the engineering team of a racing team. That recording is valuable and it has important information. You might watch the recording and is there a presentation? I am not sharing the presentation with you. I'm just, yes, of course, I'm recording the, I'm sorry about that. My apologies. Yeah, you can see it now. Better? Okay, let's go over the slides again for a minute so you know. So this was the list that we had at the beginning. And this is the name of the talk for all of you. This is going to go into YouTube and it's going to be my wall of shame forever, just so you know. So the 3 points that I mentioned, measuring intuition, ego, and emotion. When it comes to measuring, this is the infamous twisted version of the quote from Donald Knapp, and this is the actual phrase that he says, right? And here is where we are. Okay, sorry, apologies about that. So metrics from observability are like a recording of a car race, are not an in-depth analysis of what's going on in the car and every time. Of course, in a racing team, this car is also going to have some metrics inside it, some devices that are going to emit information, and professional racing teams tend to use that. They get live telemetry from the car, and they can use that later on to improve on the car. But this is the thing. Benchmarking, it's more like a test bench, the thing that you're seeing on the screen right now. When you put the car there, and you get and you get the ability to measure very precisely how the car is reacting to certain pressure that you're applying to this. Accelerating, applying resistance, the rods that you see there are able to offer resistance to the wheels, so you can simulate certain situations in the real world, and it gives you very precise metrics over very few variables that are changing. Make sense so far? Especially now with the slides? Yeah, cool, great. I'm going to share the screen itself because it's demo time. It's time to see code and see actual tools working. And there we go. Awesome. So I can take the slides out and not the, sorry, take this out and let's start with the actual demo. Here we go. So I'm going to present you this atrocious piece of something that someone might dare to call software. Please bear with me here. This is an abstraction over some kind of in-memory storage. Right? And this, what it's going to do is being able to store data. In this case, they're going to be integers. And sorry. And they are going to be based on an index. If only we have an abstraction like that in .NET, don't we? Yeah, okay. I'm just wrapping an array in a class. But I'm going over this because this program has some difficulties, some challenges that look like challenges that I have faced in real world projects. Okay, so as you can see here, this is a class that it's able to initialize an array for storage. Okay, we have a method that is called store that has a safeguard that will not throw an out of index exception. Will just ignore the value you're trying to store. And it's able to add. It has an overload of the add, so you can have two pieces of storage and you can one or the other and they're merged together into an array. So far so good? Makes sense? I mean, it doesn't because you can directly do this with the language, but that's the idea behind the abstraction, isn't it? And because I'm having performance problems with this piece of code, because my metrics, my boards show me that there was an issue with this, what I did is I wrote a small piece of code that will just generate 1,000 of them. Make sense? Yeah? Okay. And what I do with this test is I just go over all of the values. I start with 0 and I will add them over and over again. And once we have done the addition, I will also store the 10 first values with sequential numbers just to make use of the store method. Yeah, I'm not validating the results just because for simplicity. So then in the program, I will just create this abstraction test. I will get a watch. I will run the test, and then I will see how much time has passed. As you can see, we're going to iterate over just 1,000 elements. I will bring the console into screen when it shows up. Here we are. 627 milliseconds, more than half a second to loop over a list of 1,000 elements. Does that sound reasonable to you? Yep. Nope. Yeah. Thumbs down. Doesn't sound reasonable. Doesn't make any sense. I mean, half a second just to iterate over a list. What's going on here? Okay, let's try and figure out what happens here. First of all, maybe this was a fluke. No? 400 milliseconds. All right. Check again. 415. Oh well, if it was a fluke, it's around 400. Okay, I could be doing this all day, but what do I get what do I get from here? Why do I get that the first one took 500 milliseconds or the other one? I don't know. Let's take a look and see if .NET offers any kind of tools that can help us see what's going on here. And to begin with, we could make this run for 40, 50 times, calculate the average. But what happens? What do? We show also the maximum and the minimum. We do a statistical analysis. Well, there's already libraries that do this. In this case, we have .NET benchmark.net, which is a well-known library. So instead of running something like this, what I could do is I could just go over here and call this framework, which is what I'm going to do straight away. So there we go, and we're going to put nothing here because this is not where you put it. You put it on the method, and on the method you put benchmark. Yeah, thank you, AI. AI is coming for your job. And what I do here in the program is instead of calling this, and you will please forgive me for just commenting this out instead of deleting it, because we might call it later. We will call it later. And what I'm going to call is called the benchmark runner. Yep. Dot run. Nope. Not that one. Thank you. Okay, that was scarily clever. Go here. So if I run this, where you're going to see, by the way, you need to run on release when you're running this kind of benchmarks, because you want to measure with the compiler optimizations that you get on a release version. And what you're going to see now, it takes a little bit because it's going to create a virtual project with the settings that I have given it, and it's going to do some warm up to make sure that everything is compiled, because as you know, .NET does just-in-time compilation, and then it will show you, it will make a calculation, it will give you the time. So the mean value, it's around 400 milliseconds, which is a mean thing to say to someone that wrote a piece of code that is just going over 1,000 elements, is taking 400 milliseconds. That's forever. That should not be like that. Any questions so far? Nope. Okay. Just so you know, the error thing is the confidence is half of the 99.9% confidence interval. This means that you can have a certain degree of confidence that if you add or subtract this amount from the mean, you're going to have 99.9% of the executions within that range. This is important, and this is the metric that is most important. Standard deviation is useful for certain things, especially when you're working on a piece of code that you're worried about the mean across time and not the vast majority of the executions. That you can live with having more outliers as long as the majority of the executions are fast. Error bars in the chart. What? Peter, can you please unmute
Would
yourself?
be the little whiskers, they call the error bars, the whiskers. If you had this graphed,
Yeah.
you'd have the little whiskers showing where it falls, as you say, in the 99%.
Little whiskers. I don't understand what you say. Can you rephrase that, please?
If you get a bar chart, you get, they call them whiskers normally. You get the little line.
Yeah. The whiskers. Yeah. Yes. Absolutely. No, that's for a normal distribution. That's a different thing. Well, it's on the same nature, but yes, it's the whiskers, but it's the real extreme of the whiskers, not what is normally taken in the normal distribution. In the normal distribution is 2.5% on each side. This is 0.05% on each side. Make sense? Yeah. Okay. Cool. So, well, we know now that it's consistent, that it fails to provide any kind of performance during that time, but we don't know what's going on yet. Okay. So what I'm going to do is I'm going to run a different thing, which is going to be So KC, and let's comment this, and let's uncomment this part. I told you I was going to use this again. So there is something called the performance counters, which is something provided by .NET by default, and we don't need additional tooling to have that. This is something that I recommend you to use when you don't know what's going on in a program, and it's was Alt F2 or Shift F2? I never remember, or maybe it's just ignoring me. Let's search. Performance profiler. Alt F2, yes, it's telling me. Okay, I swear I was pressing Alt F2. Okay, so we're going to go and run the .NET counters tool. This is what it's going to give us. Oh, well, that's not very useful because it was very short. Need to put this on a loop. Give me a second. Yeah, for loop. Okay, let's make it 200 times. And test.add, right. You can leave this place, thank you. And now that I have this, yeah, now Alt F2 worked for some reason. So you can leave, thank you. Now run this 200 times, which is going to be 100 seconds is a lot of time. Let's rethink that and just run it 20 times. Everything is saved, yes, correct, fantastic. Right, and away we go. Now it should be running, and we're getting some metrics here. Okay, it took around 8 seconds to run 20 times. That's reasonable. So the metric that I want to show you here, and the one that it's quite important, is this one. So we're having something called percentage time in garbage collection since last garbage collection. What is garbage collection? Garbage collection is a tool that helps frees you for having to worry about memory allocations in your system. Before we had high-level languages, we had to worry about the space in memory we were using, and we had to keep track of it and release it. Languages that like .NET, JavaScript, they have systems that are in the background just cleaning up, and they're called garbage collectors because you're just cleaning up the garbage. They're just cleaning up every object that you're no longer tracking. And this is a bad number. Anything above, 0% is ideal, but anything over 5%, it's something that piles up, and it piles up at scale. GC weight means that for some reason, we were unable to allocate an object, so the garbage collector needs to make a space for us. And in order to make space, it needs to tell the running thread to freeze. Freeze. This doesn't mean that the process is not running. This means that the core that you're using from your processor cannot be used by anything else until you're done. And if you have enough processes doing this, you can have 100% CPU utilization showing in your dashboard in Grafana or your New Relic thing, while your actual CPU usage is less than 1%. And I have seen this. I have seen usage of CPU that was never over actual 10%, but it will show us 100% CPU utilization. That is because a frozen thread counts as using 100% of a core. Make sense? Yeah? Cool. So what can we do about this? What can we do about this? Well, one thing is that we can start guessing, which is normally what we do with our instincts. And when we look at the code, we are going to see some things that pop up immediately. Some things that might trigger you. I'm going to restore the benchmark. Okay. And I am going to modify this to make it run slightly faster. This is going to give us less statistical accuracy. So try not to do this for a benchmark that you are going to use to measure whether a change you have made is worth committing. But for the sake of the presentation, we are going to make it a short run job. This is okay for quickly iterating, but in order to trust the results, I recommend you to not use this thing. Okay? So I run this and you're going to see that it runs significantly faster. This is not the kind of thing that you put on a pipeline, by the way, to keep track of what your system is doing. You have observability for that. This is an exploratory process, and you will find yourself taking notes or writing stuff down in Notepad. You can see that the error now is significantly higher because we haven't run this enough times. I know that for this program, this is not going to be a problem. So we're going to leave this over there. Okay, so we leave, and then I'm going to take a look at our store extraction. And the first thing that we are going to do is, well, the ID is already suggesting stuff. So this is telling me that I should use IEnumerable, no? Yes? Okay, so I make this change. Oh, wait a second. I said that you were going to be using Notepad to save the stuff, no? I said that, but then I didn't actually save it. So, oh, it seems that I closed the console without saving the result. So let's run it again. Okay, I mean, we have just made one little change. It's not going to change performance at all. Or will it? Oh, I didn't time that correctly. Well, I have already spoiled the surprise, but you are going to see that now it's taking 500 milliseconds. Ignore the error matching. 500 milliseconds. Okay, remember when it said that intuitive guesses fail? Who wants to give me a wrong answer as to why this is happening? It's assumed. Come on, nobody? The takers? Okay, my first intuitions when I saw something like this happen, and this happened to me, I changed something that it was an array to an IEnumerable, and it had a severe performance improvement. My guess was a virtual call and allocations. I didn't actually understand what was going on. How was it possible that just by accessing a lower level interface, I'm already using for each on the arrays? Why changing this, changing to this, will cause these different results? Dun, dun, dun. Hey, we're back to 400. What's going on? Let me show you, because this is a very interesting one and this is a good discovery. And if you leave this place, if you leave this talk today only with this information, you will have learned something that might be useful, because this is something that might hit you. Let's uncomment this one. And we are going to run with a different performance counter. Shift, Alt, I don't know how to type anymore. And we have the .NET Object Allocation Tracing. This is a different tool, and this is what it does. Is it, when you run your program, it keeps track of every single object that you are allocating in your system, and it lets you run an analysis of where these objects are being allocated. I am going to cheat, and I'm going to go straight away to the results, because I want you to take a look at what's going on. You see, it took 23 seconds. This is very, very expensive. So when you're running a program like this, make sure that you don't run it for too long. So this is the insights are taking you that we have high fragmentation in the large object heap, which is where we store the largest objects that our program is allocating, and also excessive generation queue collections. This is a major issue. But if we go at the allocations, we are going to see that one of the objects that is being allocated the most is this one, sset generic array enumerator. This is one of the worst enemies of performance you can face in situations like this. The reason for this is because arrays are really not generic IEnumerables. They never were at the beginning. And when the IEnumerable generic interface was introduced in .NET, there was a need for a layer, something that will help us access the IEnumerable interface in arrays. And that object, when you access the enumerable interface of an array through the IEnumerable interface without knowing that the object is an array, you are going to allocate that object. That object is very expensive. As you saw, it took performance down by 25%. It causes a lot of memory pressure. It's important to know these kind of things. LINQ, modern LINQ, mitigates that. So if I, instead of using a for each, I were to use LINQ, LINQ does some introspection and is able to understand that it's using an array. So will not use the IEnumerable, it will access this through index, but not always, because if you're using joins or groupings, it will still allocate the enumerable thing. So if you will excuse me, I'm going to undo this change because it's not helping us in any way. And what we can get from this is that we are allocating a lot of lists, and we are allocating a lot of really large integer arrays. And you can see them here. Make sense? What we're getting from these results is coherent? Yeah. So what is the problem? What's going on? What do we do about this? Well, one of the things that I did first when I faced something similar to this, that we were iterating a lot, I converted this to a struct. I'm not going to use time of this. We are going to see a tiny performance improvement if I convert this class to struct. Okay. And also, funny thing is that I do a performance improvement. You might think that this calling the constructor and accessing the values might have an impact in performance, and you might be tempted to violate encapsulation in order to access this for performance reasons. Normally, in structs, in situations like this, it has no impact whatsoever. There are very specific situations where it might happen. We're not going to go into them now because we will be here forever. But making this struct will make an improvement because classes are stored in the heap. Structs are stored in the stack, which means there's no garbage collection when you get rid of them. You just delete the whole stack. Okay, adding to a list duplicates its capacity. It's in a range. Okay. Yes, no, maybe, perhaps. If you look at the implementation of list right now, yeah, set capacity up front is a very, very sensitive thing to do. Absolutely. So let's do that. Let's do that. That was not planned, but let's do that. What is going to happen if I do one length plus, oh, wrong key, sorry. Here we are. Plus idiot. Other. What's there we are. Let's hit it again. Let's see what the benchmark tells us. 600 seconds. Oh, my bad. Sorry. Getting there. That was a cool move, Jacob. I expect an improvement. Yeah, it's a significant improvement, but it's still quite expensive. The resizing was bad. The resizing was really bad. And if we look at the allocations themselves, you're going to see that the sizes, if we sort them by type, the sizes are not doubled when they're being allocated. You see it here? They're not doubling. That's something that I painfully discovered. The doubling thing that you mentioned happens in dictionaries. For some reason, dictionaries, when you start adding stuff, if you go over the current capacity, it will resize its internal arrays to double the size. List, on the other hand, they create a new array with one extra element, will copy the array one to the other, which is surprisingly less expensive than you might think, but it's still as horrible as it sounds, and then we'll add another one, and it will allocate another large array, and it will add the element. It's a party. So good one, Jaco, and we save a lot there, but we can do better. And there is a technique. So the arrays here are completely unavoidable. We cannot help it because that's the whole point of the thing. So how do we prevent something like this? There is a technique to prevent this kind of large allocation, and it's called object pooling. Object pooling, it derives from one major tenet of performance.net, and is that objects should be allocated on generation 0 or should never be allocated. What's generation 0, you may ask? Let me show you. I go here and I add this other thing. Oh, thank you, AI, to the benchmark, the memory diagnoser. And this is going to give us the amount of collections in generation 0, 1, and 2 that we are doing per every 1,000 operations. And generation 0 are pretty much free collecting, well, pretty much free, but they're very cheap. And collecting in generation 2, in generation 1, it's slightly more expensive, but it's still not terrible. But generation 2 collections are the ones that might end up freezing all of your threads. And this is allocating 1.24 gigabytes of RAM just for 1,000 elements. Okay. Let me undo all of the changes we have made and move to another branch, because this might take a minute or two to get there. So I'm going to check out changes, or type very fast and you didn't see me. And what I'm going to show you now is the change that we have made here with a typo. Thank you. I'm not going to rename it. I'm going to leave the typo there just to trigger you. This is what is called an array pool. This is provided by the CLR, and it's a collection of arrays that once you're done with them, you return them. So they get allocated there forever. That's what this means. Objects should be collected on generation 0 or should never be collected. I also turn this into struct, so the abstractions themselves are not allocated in memory ever. They go to the stack. There's one problem with this, is that the pool asks you for a minimum length. This is a source of problems if you're not aware of that. Minimum length, which means if you ask for an array of 1,000 elements, you might get an array of 500,000 elements. It's quite important, and it's an order of magnitude error if you assume that the array is going to be the size you're asking for. How do you handle that? Well, the abstraction needs to keep track also of the length. This is what I'm doing here. So I'm doing exactly the same thing. Instead, I'm using the length to iterate over the arrays and build the new storage with the new length. Make sense? Yep. Okay. How will this perform compared with the 300 milliseconds with the improvement that Jaco suggested? Why not use it dot length? I'll take a, because the arrays that are coming from an array pool you don't know the size beforehand. So if you use dot length, if you ask for an array of 1,000 elements, you might get an array of 1,000,000 elements. Make sense? Did I answer your question? Yes? Okay, cool. Well, microseconds, 200 microseconds instead of 300 milliseconds. And comparatively speaking, and the metaphor that I'm about to use is calculated for the 400 milliseconds instead of 200. But the dimension, the difference between this and the execution before is the difference between 3.5 meters and the distance to the moon. Pretty much when it comes to high. Oh, sorry, I just mixed up the metaphor. That metaphor is for something else. It's thinking that you can swim from the UK to the United States. That thinking that that distance is swimmable. That's the difference. I just mixed up the metaphor, sorry. And okay, so we're done with the demo. We're done with the demo. We go back to the slides. Yay, everybody loves the slides, don't you? Let's go here and let's go with ELF12 and go into center view. Great. So intuition, what happens with intuitions here, and why I mentioned that we might be slightly impaired when it comes to this kind of stuff. Okay, what happens with intuition? There's something called the expert intuition. It is something that, for example, when you are driving, you want to, so you have muscle memory and you want to brake, and what your brain does is it presses the brake pedal. No? Makes sense so far? You don't have to think on braking. You don't have to think on putting your foot there. You just think on braking and your body responds to that. There is a higher level version of that, which is, Peter, will you be a volunteer here?
Yep, sure thing.
They're not going to be hard questions. They're going to be easy, okay? 2 plus 2.
4.
Okay, 317 plus 13.
330.
Yes, took a second. You had to think about it. Well, 2 plus 2 just came. Because these simple operations, when we learn the multiplication tables and all that, we just do them instantly in our brain. This is what is called the expert intuition. This is a similar to muscle memory, and matter of fact, plays hand in hand with muscle memory. That's why when you watch combat sports, you watch boxing, and you think that you might be able to do that, then you go to a gym and you start training, and when you're sparring with one of the guys that is actually an amateur boxing and does real boxing, he gives you swabbing of your life. And not only that, is that you always have the impression that you almost had it there, but you didn't, because you have to think that that person is making an opening, and you have to think that you want to throw a punch. That person just thinks opening, and it's there. That's the expert intuition. That's how this thing works. In order to develop an expert intuition, you need 3 factors. This is not something I'm making up. This is coming from Daniel Kahneman's works, and there's a fantastic book called Thinking Fast and Slow. Beware if you're reading it. I forgot the chapter that it is, but there's one chapter that is declared incorrect because new science has proven that chapter to be wrong. The rest of the book is still worth reading. And one of the chapters goes precisely on how expert intuitions are developed. The conditions for an expert intuition to happen are that the time between the decision and the consequence is short, that the cause of the consequence is the decision and is evident to you, and that there is enough repetition for the intuition to take hold. So something that happens a lot of times, you clearly suffer when you make a mistake, and you clearly benefit when you get it right. And it happens in a brief period of time. This is useful. This is really, really, really useful where you're hitting nails with a hammer, because your brain learns not to put your finger on top of the hammer. This is very useful when something is red and bright and you touch it, because you get burned once. You don't touch something that is red and bright ever again because you know that it's really hot. Well, some people do it every now and then, mea culpa, but it will still happen. What's the thing? This thing can play against us. And this is very important. This happens with gambling. You make a bet that is statistically a bad bet, but you win. So next time you see a situation like that, your lizard brain says, hey, it's like the last time. And you keep making bets that make you lose money. And if you have a strong hand and you don't bet because the last time you bet with a strong hand you lost, you will lose your statistical edge and eventually lose the game. Our instincts play against us in certain environments. So there are environments in software development where your instincts can play really well. One example is developing with TDD, because the three conditions are met. The red-green refactor cycle. You make a change, you immediately see if you have improved, if you have come closer to the answer. That's why TDD makes it's useful to develop software, because it gives you short feedback loop and it doesn't trick you. In general, when you make a change, what you see, it correlates with the it correlates. It's really a consequence of the decision you made. Software architecture, it's really not a place where you can follow your instincts, because normally you make a design in software architecture, you make this beautiful mirror board with all arrows connecting, you implement, you go to production, something breaks. There is no direct connection with the brilliant idea you had a month ago, but that brilliant idea maybe it wasn't that good. And because you don't repeat that enough, because you don't make big architectural decisions often enough, you also don't develop those instincts. But when you've done architecture long enough, you begin to develop instincts. They're just not correct. There's a mitigation about that, by the way, when it comes to software architecture. It's called formal methods. You can design a mathematical model of your system, and it will give you immediate feedback on the design level. And that will help you be a better instinctive architect. Okay. Generating pictures for a slide with AI. That's not a good place where your instincts will help you. Okay. I was trying to have goblins fixing a car here, and I really thought that this one was going to be the good one. And that really doesn't look like a goblin fixing a car. Okay. Areas where instincts may not help you also. You guess right. That's why we're here. Performance tuning. Yeah, I got eventually the right. But performance tuning is one of these examples, because you might make improvements and for the wrong reasons, based on the wrong assumptions, you make a change and the change makes the system behave better. And you begin to think that that is a good move. And if you do it enough, you will find that now your brain resists the idea of being wrong about that. And one day, those assumptions are going to be proven wrong, and you're going to have a hard time proving yourself, getting yourself out of that. And finally, we're in the final stretch: ego and emotion. Two things to love yourself. Remember always, you are not your code. You are not how often you get it right. Okay, repeat this to yourself and forgive yourself about being wrong when you're working with performance, because you are going to be wrong in the vast majority of your assumptions. You're going to spend days making this change that finally is going to improve the system. You're going to finish it, you're going to benchmarking, and you're going to make performance worse by 20 something percent, and you will be baffled as to why this is happening. So be ready to throw away code. Be ready to accept that you're going to make mistakes. And unfortunately, I don't have an answer for you on this. It doesn't get any easier. It's just something that you have to accept, that this is going to slap you in the face. And something else to take into account when it comes to emotion. In nature, if you stop and think when you're hungry, you starve. Why this happens? It's because when we develop these brains of us that allows us to build computers and all of this stuff, we also became weaker. And there were situations of life of that where we will stop and think. And that was a terrible decision. So we have a mechanism that inhibits our ability to think when we are in certain situations that are abnormal. We become dumber. That's why they tell you you shouldn't go do groceries when you're hungry. It's not because the hunger makes you buy more, it's because the hunger makes you dumber. And you make stupid purchases, things that you know you shouldn't be buying. But your brain slows down because you're hungry, and if you don't eat, you die, which is not the case. Well, this also works because when you're worried about your people, they get hunted. And when you're scared, you get hunted. And when you identify yourself with your code, and when you measure your worth by getting it right, you are going to resist the idea of throwing away your code or to accept that you were wrong. And that is going to play against you all along. And sadly, I also don't have an answer for that. It's just something that you have to accept already, that you have to forgive yourself for the mistakes you're going to make along the road and try to move on past that. And that's it. I wanted to show more pictures because I had so much fun trying to fix the thing. Any questions that you have now about this stuff? Yeah, Peter?
I'm going to go on in. I did like the way you presented this with, what improvements can we make? And the obvious one, pre-allocate, made an improvement. And then you circle back round to say, yeah, obviously, if you don't make the measurements, you're going to make the choices that don't improve.
Mm-hmm.
If you were given one of the very typical vast legacy systems with this sort of thing in it and are told to increase performance, whereabouts would you think about benchmarking something like that?
Something like?
The typical vast legacy system. You can't easily get in and drive into individual parts of the benchmarking. What sort of divide and conquer approach do you use to drive that down?
You're not going to like the answers. Well, first of all, you do need observability. That's one of the things that any way you can provide some degree of what's going on, how long is it taking to execute something, you do need observability there. That's one critical element that I will recommend you to go on about. And once you get observability there and you have more or less an idea of which are the hotspots, which are the places where the thing is clogging down, the next step is, you know how hedgehogs make love?
Sorry?
You know how hedgehogs, the small rat-like animals have spikes, hedgehogs?
Yeah.
Yeah.
Very carefully.
Yeah, very carefully. Yeah, you're pretty much trying to get on top of something that has a lot of spikes, and you're going to come in with a lot of spikes yourself because observability harms. Yeah. Try to determine the hot path, then do the benchmarking on those paths. And when a system is massive and it's really hard to decouple, the answer to that is it's very hard to do that. The good news is that tooling like this, when you run them, they really don't care that much of what's running underneath. So you can be quite brutal about that and just run the benchmark on top of the whole thing with IO in a test environment and get a general idea of what's going on and get proper metrics. That's one thing. Second thing is that performance counters are always available. any system that runs .NET, it's able to capture is able to capture performance counters. So you can always get metrics for that. And there's also the possibility of tracing. And if you're running modern.NET, it shouldn't be hard to create an environment where you run the code and you get a list of which methods are taking the most time and how often they're being executed. And it's not as magical as it sounds. So if all is in the same code base, it actually works better. But once you start having packages and packages that are called packages, it gets a bit muddy. And sometimes the numbers don't add up, and you have to understand that if you are calling a method and it's taking a certain amount of time, but the methods called underneath, they don't add up to the whole time, there's some time lost there that you're not tracking, that your tracing is not getting. So sometimes you have to go, sometimes you have to go and benchmark the library. So if you know that you're calling the library 6,000 times in one execution, and then you benchmark the library and you see that the library with the same data you're calling it with, it's take X time, you multiply that and say, oh, okay, this is my missing time. This is what it is. So it's like, yeah. Thank you, Jaco. But that's pretty much it. You have to explore, investigate, and gather as much data as you want. And going back to the quote from Sherlock Holmes is that you cannot. The issue with this kind of things is that you don't really know whether you have finished gathering all the evidence. And you have already developed some theories without having all the evidence because you didn't realize because there's too much noise.
The noise is always an interesting one, yes.
Yeah. So if there's one thing that I have seen is that memory allocation tends to be a usual suspect. So it's just quite often, especially if you're working with arrays, and bear in mind that all collections are arrays underneath. If you're working with arrays, there's a good chance you're doing some memory allocation stuff. That's important to know, that you have large objects. Arrays are pretty much the only object that you can allocate in .NET that is really large. There are others, but it's mostly an array. So that's at least you got that going. But measure, because your intuitions are highly likely to fail. Any more questions? Nope. Well, thank you for being here, and sorry for the problem with the recording. Just for the people in YouTube watching this, the reason is that Google decided that we could not record this call, so it had to be recorded with OBS improvising on the spot. And well, see you next time. Bye. Thanks a lot.